Hello everyone, so today is the first lecture of quantum mechanics for CSIR NET, and today I will be covering the extreme basics of quantum mechanics. So we start with the Heisenberg's uncertainty principle. The Heisenberg's uncertainty principle. I will just teach those portions that are important for the exam. So Heisenberg's uncertainty principle, as you know, I will not go into the details of that. That is equal to delta x delta px, that is the uncertainty in the position and the uncertainty in momentum, multiplied is greater than equal to h cut divided by 2. This is the Heisenberg's uncertainty principle, as you know. Now we move over to the time independent Schrodinger equation. We move over to the time independent Schrodinger equation. The time independent Schrodinger equation is a very important thing because in the next class we are going to study potential well, infinite potential well. So for infinite potential wells, the time independent Schrodinger equation is extremely necessary, which goes as minus h cut square divided by 2m d2 psi dx2 plus v psi is equal to e psi. This is the time independent Schrodinger equation. This is very important to remember. So now we have psi, which is our wave function. But psi itself is complex and it does not carry any specific meaning. What carries a specific meaning is psi star psi, that is also written as mod of psi square, that is also written as rho, or known as the probability density of finding the electron at a particular area, in a particular volume. So P of x, that is the probability of finding the electron, is written as integration over rho dv, because rho is dp of x dv. Now this interpretation of psi star psi is the probability density rho. This interpretation is known as the Born interpretation. Now we have P of x is equal to integration rho dv. So therefore, now if I talk about the properties of psi, then very important to notice: number one, psi is single valued. Number two, psi is convergent, that is, it has a finite value in a specific domain. If the potential that we are considering is a finite potential, then psi is continuous and d psi dx, that is the first derivative of psi, is discontinuous. Whereas if the potential is infinite, the potential that we are considering, then psi is continuous. In case of infinite potential, psi is continuous and d psi dx is discontinuous. In case of a finite potential, psi is continuous and d psi dx is also continuous. We will see an example of this in infinite square well, and we will see an application of this while we study the delta function potential. Now something which is important is the property of normalization. Normalization means that integration dp of x is equal to, we wrote down, this is equal to integration, this is p of x is equal to integration rho dv, that is equal to integration psi star psi dv, that is equal to integration mod of psi square dv. So integration minus infinity to infinity psi star psi dv should be equal to 1 because the total probability should be equal to 1. This is the property of normalization. And if I have something like, I am introducing the infinite potential well here, if I have a potential like this, that is V is equal to 0 in a specific region, say from 0 less than equal to x less than equal to a, and I have potential is infinity otherwise, that is we have a potential well like this, where this represents the potential, and this represents x, this is v of x. In that case we have the potential is infinite everywhere else and finite only from 0 to a. Therefore here we can write integration 0 to a psi star psi dv is equal to 1. Integration 0 to a psi star psi dv is equal to 1 for bound particle cases. So I hope this lecture was useful. I will return with infinite square well and then the delta function potential in the next few classes. Hope you are preparing well for CSIR NET, and thank you for looking at this video. So please do consider subscribing to the channel for more videos in the future. Thank you.